Hello, welcome to video 15 in the lecture Advanced Mathematic Modeling. And in this lecture I want to give you one final application for this technique of the variable transform. And now I want to look at this first question, that we have a given transform and want to know what's the change of a probability distribution. And I want to do this because I want to take this special example that this f is a log transform. So we say we have a random variable, and I want to make a log transformed variable, and I want to know what's the distribution of a log transformed variable. So we're looking at the distribution of a log transformed random variable. Why would we be interested in this? And the reason is that the log transform is an important transformation in practice if we have random variables which go over many orders of magnitude. So if we have random variables that go over many orders of magnitude here. And then it sometimes makes sense to look at new variables y, which are just log transformed variables of x. And then this y don't scatter so much. And this is, for example, important as another technique to estimate the probability distribution. Here we showed you if we have variables which go over many orders of magnitude. Yeah. Sometimes you can try to make bins which increase more and more in bin size when x gets larger. But another situation would be, instead of making this uniformly distributed bins, you could just transform this scattered variable x by log transform to another variable which is not moving so much. Then you can just do a normal histogram. You don't have to tune your histograms, and then you transform back. But then, if you want to do this, you need to know what if we now estimate by our algorithm our histogram of p of y, what is then the distribution of p of x? So how does this work in practice? So in practice, so we have our x, this scatters a lot. Then in the next step we go over y equals log x. This y behaves more normally. We can make a histogram. We estimate our q of y here by normal histogram. And now the question is, what is our p of x? Because that was the thing we were interested in. Okay? And so now we need to know how a probability distribution p of x transforms under this transformation. Now we remember what was our formula to do this. We said that the density of the transformed variable is the original density times the derivative dx over dy. And now this p of x is not uniformly, this uniform assumption we took in the previous examples where we used inputs from a random number generator. And so now, and then what is the variable transform? Y equals, and actually here I always take for simplicity, the natural logarithm. That will, so because then we can take the derivative more easy. Now maybe a word to this. When I plot data on a double logarithmic axis, it makes sense to take a log 10. Because then I see orders of magnitude. Maybe here I have 10, 100, 1,000, 10,000, and also here 10, 1, 10, 100, 10,000. So taking the logarithmic log 10 helps a lot in plotting data because we directly see the value of a number. So in a log-log plot I usually take log 10. But now in this calculation here it's really important that you take the natural logarithm, and this means maybe later for plotting I have then to transform this back to a log 10. But now we assume our variable transform is a natural logarithm. So if we use this, then we can calculate here further. This is p of x divided by dy over dx. Now the derivative of the logarithm is 1 over x, and so this is x times p of x. Now if we use this transform, right? So for this transform, q of y equals x times p of x. And now if we want to make a logarithm of this, because now we want to plot this on a logarithmic. So like first, I mean, I should say this would be enough to now we have already calculated what we want. So now, like, you know, that was our problem. We had x, we made the log transform, made a histogram, then we have q of y, and with this formula here I can calculate p of x. But very often I want to have this logarithmic, and then you see that we can divide on both sides by x, and then we have the logarithm of p of x equals the logarithm of q of y, and then we have minus the logarithm of x, and the logarithm of x is y. So we have this formula. So in normal numbers we multiply by a variable, so the transform of the probability densities is just the density times x, but if we plot the log of these, we just have to subtract this y. And so that's why, so like now if we now have our histogram and we plot it logarithmically, and then I just have to subtract this y. So this formula's the calculation is quite simple, but you will see in the exercises when you want to do this in computer code, you can be easily confused with these variable transforms. And if you are confused, don't worry, this happened to quite a lot of people. So this happens also to me when I do this. Usually I make 2 or 3 mistakes in my code until I have this correct. So let's say we have our a vector x is a vector of our sample. Our random variables. So now we calculate the computer log of x, so this makes a natural logarithm, and then we make a histogram, for example in MATLAB. And we don't plot this directly, but we let the algorithm give us the bins, and let's give us the weights. So this gives us our distribution of the log transformed variables, the position bin and weight. So and then we can calculate now the exponential bins. This is just the exponential function over the vector of the bin position. And now we calculate our new variable, this log of this here. So we calculate log, the new variable log p. And this variable, this is again a vector, this is the log of our weights minus the bins. So this calculates the log of our weights of the histogram minus the bins, because the bins were the positions. This is log p. And now we can plot our exponential of our bins versus our log p variable. And this then makes a plot of our log transformed p of x. And this is in one of the homeworks where you use the log transform, something like this. This could be the base of the code you use in order to obtain the histogram of a log transformed variable. Okay, so that's for now. So now we have seen a lot of examples of this variable transforms where I have to agree. It's maybe sometimes when you use it first time it's a bit confusing. And so now we mostly have covered the base of all this probability theory. In the next videos I want to show you some more advanced method of generating functions, and maybe this is now the point where most of you will learn something new. At least I hope this, to start with some more advanced and modern techniques. For in the moment, thank you.